Good afternoon. I'm happy to be here. My name is Janis Keuper. I come from the Competence Center for High Performance Computing from the Fraunhofer Institute in Kaiserslautern, Germany. So some of you might know us because we're actually doing seismic software. Prestack Pro is one of our products. Today I'm going to talk about deep learning. Now, we've seen the talk from Deborah before, and she already indicated the hype we already have about deep learning and machine learning in particular. No matter if you're talking about self-driving cars, game-playing computers, voice recognition, and all sorts of things, deep learning is the technology behind it that actually drives all this hype. And this hype has become huge. It has become so huge that it actually, on the way, is destroying the science of it, because we're moving so fast that peer review actually died for deep learning. This is true. Everyone's pushing their results online the minute they have it, and then they're moving on. So we're moving extremely fast, and the question is, will this actually affect your community? So is the oil and gas, especially when we're talking about seismic imaging, affected by this trend? Yes, I can tell you this. There are a lot of projects starting right now using deep learning methods for filtering in pre-stack processing, for object detection, maybe fault detection, automatic fault detection, for improving your migrations, and so on and so on. We have some projects that are going on. I would have loved to show you some pictures, but unfortunately, your community has a very different approach than the machine learning community I come from, where everyone shares everything. Here, I'm not even allowed to show you a single picture. I'm sorry for that. So I will focus on the part you will have to face when you actually start such a project of your own. And for seismic imaging, you have tons of data, at least from a deep learning perspective. So we're starting up maybe with 100 terabytes of data in your learning project. In order to make this work, you actually have to somehow scale this. And in this talk, I will show that it's actually not so easy to do that, even though some of the hardware vendors, some of them might be in the room, may want you to believe if you just buy enough GPUs, the problem will disappear. The reality is more complicated than that. So now this is still not. OK, quick overview. Just to get you up to speed, a very, very brief, a very compact review of what actually is meant with deep learning and what the distribution and parallelization of the problem actually is. And then I come to the central issues of scalability, which will look very familiar to anyone from HPC, because mainly this is a communication-bound and IO-bound problem with some specific numerical problems that needs to be solved. And in the end, we will look at some implications for your seismic applications. This talk is mainly based on the paper we presented. No, it's working. We presented last year's Supercomputing. So if you want to go into technical details, I may refer you to this paper. OK, wrong direction. Now, deep learning in a nutshell. Most people will associate deep learning with deep neural networks, DNNs. In theory, this is not entirely true. Deep neural networks are just simply the only way we know how to implement the deep learning scheme right now. That actually might change as soon as someone's coming up with a better algorithm. But as of now, we have deep neural networks. And at a very abstract level, a deep neural network is nothing but a directed, sometimes acyclic. In my examples here, we'll refer to this case, graph, which has nodes that represent some compute entities. We'll talk about this in a second. And the edges just define the data flow through the graph. If you're training the network, actually means flowing data from top to bottom and back. We will see that in a second. And inference of the network is just running data through the network. So usually you see a simplification like this which I always call the layered cake. I will come to this. I will use the simplification throughout this talk. Actually, so it's not even correct, because as you can see here, we can have more complex graphs, but for the issues I'm talking about today, that actually doesn't matter. Now, if you look at the compute entities, the most famous compute entity is the perceptron layer. This is what most people have in mind if they talk about deep neural networks. You actually have neurons that are interconnected, like in the brain, and they're learning some function of weights, and then they learn to approximate some highly nonlinear function. But this is only half of the truth. Actually, a deep neural network nowadays mostly consists of other things than neurons. There are literally hundreds of different types of layers, the computational units, that actually compute different things, from convolutional filters to normalization to data simplification to regularization, and so on and so on. So there are many, many, many different compute entities we actually have to face. And it will turn out in the end of the talk that the actual neurons are causing most of the problems, and we're trying to get rid of them, after all. So, training a neural network, and I'm going through this real quick, actually settles down to the mathematical problem of solving a highly non-convex function in a very high-dimensional space. So it could be billions of dimensions, huge space, non-convex, so this is a very hard problem. It's actually an NP-hard problem, so we actually end up with some kind of approximation of this problem, and this is not solved directly nor completely correct. To do that, people usually use gradient descent methods, which are very simple. Most, at least in Germany, you learn this like in 10th grade, Newton's method. And actually, that's what it is, gradient descent. So what you do, you feed forward, put your data through the network, compute some difference to the real answer, and then propagate the gradient back through the network and do some small updates. And you do that in a stochastic way, so you're not using all of the 100 terabyte of the data at once, just one small chunk, which is called the batch. And you run this batch down, compute the gradient, and propagate the gradient back through the network. Very, very simple algorithm. So there are some variations to this, but for our scalability issue, it actually doesn't matter which kind of more complex variation of this algorithm you're using. So the problem with that is, it's actually a very simple algorithm, but it's inherently sequential. So you cannot move one step before the other step has been computed. So once you're here, you move one batch through the network, compute one gradient, make one step update step, then you move the next batch, and so on and so on. The only way to speed this up is to either make faster updates or to make larger steps. That are the only two ways to actually speed up this algorithm. And both of them are problematic. So, parallelization plays a huge role in deep learning. If you are following this, GPUs are the dominant compute resource used in this area. And that actually comes from that part which I will call the internal parallelization. Now, for each compute entity, the layers, we have to perform some sort of computation. Some of these computations are very cheap. Others are very, very expensive. And the most expensive ones are actually melted down to dense matrix multiplications of very large matrices. So this is well understood in HPC, so we have the standard implementation. So basically what you see are here blast operations. You have your math kernel libraries for CPUs. You have the equivalent versions for GPUs and so on. So you know how to parallelize these operations on your local node. This is very simple and very effective, and the main reason why GPUs are so effective in this area. The other part is that we actually also can use task parallelization in these layers. For some of the operations, especially for the filter operations in the convolutional neural networks, you can compute several of these filters in parallel, very simple task parallelization. And this is one part where NVIDIA has been putting a lot of work in helping the community to get faster. Now, the second type of parallelization is what I call the external parallelization. Now, assume you want to parallelize the problem over several nodes. The common approach is a simple data parallelization. So I take my batches of data in one iteration step. I split them from some master and feed them forward through several worker nodes who are actually having the same copy of the entire model. Very, very simple. You have a feed forward, you compute your local gradient, the local gradient is sent back to the master, and the master is accumulating the model and then distributing the model to all workers, and you make the next step. Very simple, very effective, but unfortunately, the speed up comes only from data parallelism. So you would actually expect this to be scaling linearly. If I can split my data, pure data parallelism should work perfect, but this is not the case. I will show you some experiments. They are based on very famous benchmarks in the community. It's the so-called ImageNet data set, which contains about 1.2 million images which have been annotated by humans. And the task is actually to label these images by content. It's a task which is considered to be solved. So neural networks can do this task better than humans. Now you ask, how is that possible? Well, this data set contains, for example, I don't know, 30 different types of birds. So I personally can distinguish 5 types of birds. So the neural network is much better than I am. And 2 different architectures. Just to give you an impression and this is not considered to be a huge problem. So this is about 200 gigabytes of raw data. So that's nothing like the 100 terabytes we're talking about for seismic imaging, maybe. 2 different network architectures which are very famous, the AlexNet and the GoogleNet. Overall, number of floating point operations to converge this model, in both cases, around 1 exa floating point operations. And this is nowadays, both are nowadays considered to be rather small networks. So now Google has come up with a network which they called outrageously large. I don't know what's going to be the next thing. Maybe there will be some hyper or things in the title. And that outrageously large network had 140 billion parameters to learn. Unbelievable, but that's not the end. So here, we are actually at 1 million or 55 million parameters. So just that's the scale difference. At the same time, we have a model size of about 250 megabytes, and this is going to be important in the next slides. Just to give you some impression on the compute time, the latest Pascal Titan X needs around 0.2 seconds per iteration, and around 400,000 iterations to converge, so you can compute this in a day, which is considered to be a rather small network. Other networks literally take weeks to converge. And this is the time you have to invest. So, of course, you want to scale this up. Now, these are some experiments we actually made on an HPC cluster with FDR InfiniBand interconnect. The GPUs are kind of old, K80s, but actually this plays in our favor in this case. And if you see at the green line, this would be linear scaling. So the general assumption would be just buy enough GPUs and plug it in your cluster, and that's it. Unfortunately, reality shows that we are not getting beyond, let's say, factor 32, no matter how much hardware we are throwing at this. And in many, many, many cases, practical relevant, we're not getting above 4 or even 8 nodes in scalability. So the question is why? The first reason, and actually is communication overhead. So in this model where I have to transfer the model to all the workers and the updates back to the master node, I have to compute the size of the model twice. Now the model is around, in this case, 250 megabytes, but the model could be even larger. At the same time, I compute this in 0.2 of a second. Now in data parallelism, the compute time will split by the number of workers, so I easily come down to hundreds of a second, while I have to transfer gigabytes of data. This doesn't add up, obvious. So how bad this is, you can shows this slide. So the solid lines are actually the time you need to communicate the model, and the dotted lines is the time you need to compute the model in the single worker nodes, and as soon as these lines cross, you're screwed and all of your expensive hardware is just waiting for data. So this doesn't scale very well. How to tackle this? Well, the first solution is always get faster interconnects, faster interconnects. So now, next generation InfiniBand. Unfortunately, interconnect bandwidth is not growing at the speed as the compute power of the GPUs. So what we see here is one example, NVLink from NVIDIA. It's their internal interconnect, so within one node to replace PCI Express, because even PCI Express with roughly, well, let's say 10 gigabytes per second in a real application environment is not fast enough to hold 4 GPUs. So even if you put 4 GPUs in one box with PCI Express, it won't scale. So this is one answer. And here you get around 30 gigabytes real bandwidth. Unfortunately, we got our DGX1 just last week, so I have no numbers for that. But I have numbers for the IBM Minsky, which is a very similar system. It's also using NVIDIA P100s, just 4 of them with NVLink. And here you can see that the blue line would be linear scaling. The red line is the theoretical speedup limit. We'll come to that in a second. And the yellow one is the actual speedup we get. So with the real speedup around 3.5, this is actually quite good. If you're using faster memory in there, it could be even faster. The same problem on a system where you put the cards in PCI Express, well, you end up just above a speedup factor of 2 for 4 cards. So that's interconnect. Of course, you can tackle this problem on the software side, and many, many people are working on this. You can influence this by model design. I will come to that in a minute. You can try to reduce the model size. We're going down with precision. Now we're at 16 bits with the latest hardware. It might even go down further. So there have been publications showing that it actually could work on a binary pattern in communication. We also try to have sparse communication, asynchronous updates, and so on. There's a lot of stuff going on in software. Actually, there are just 2 projects of our own. Café is one of the large deep learning frameworks. We have our own version of that. Here we're trying to do communication with reduction trees, overlay of compute and communication, and some other optimizations. If you're interested in that, we'll have a poster tomorrow with the technical details. I will just skip over that. And also on the poster, we will have our other project, which is trying to have a new asynchronous optimization algorithm, which we're not the first ones to try, which is very tricky to do. But we have some new approaches. So basically, you're trying to reduce the communication on a need-to-know basis and not wait for updates, just keep computing, which scales much better. But we did all of these improvements and looked at the results, and we got a bit better with the scalability, but unfortunately, we were still not there where we want to be. The question is why? And so we did a simple experiment and said, well, let's see what would happen if we solve the communication problem, just assume, and see what would happen. And now, we simulated that communication was free. You can do that by just splitting the problems and just keep computing the updates without building the actual model, and see how long it takes for the single worker to do the computation. And what you see there is also quite discouraging and somehow unexpected, because it doesn't scale much beyond 32 workers anymore. And the main reason for that is quite tricky and somehow unsolvable. To understand that, we need to take a look at the different compute layers and how much time is actually spent in the different compute layers of a network. So now you might not know what all these different layer types mean, but it's clearly obvious that there's one type which is dominating the compute time. And that's the so-called inner product. And the inner product layer is the traditional neural network layer. So all these neurons, maybe thousands of them, everyone connected with everyone, that's the thing that's actually costing so much. And if we try to scale this up, this is even getting more and more impact. So if you look at this from the scalability side, it's even worse. If you look at all the layers, they scale almost perfectly linear. But the one that's taking all the compute time is not. And that's really devastating. On the GPU, don't be irritated by these lines here. For many, many layers, the computation time on the GPU is so low that actually the on and offloading is taking most of the time. So basically what you see is the constant time, which is the on and offloading of the data to the GPU. But again, you have poor scalability here. Now, the inner product layer is a huge matrix multiplication. The size of the matrix is actually given by the layout, by the number of neurons you have in the layer and the layer below, and the size of the training samples you are putting through. And you can see here that one dimension actually is the number of training samples, which is much, much lower than the number of neurons. So you might choose to have 1 million neurons, but only to push 256 training samples through that. So that gives you a very skinny matrix. And we all know that skinny matrices don't behave the way we like it. And if we just plot here how long the matrix multiplication takes, we see that this will drop. Actually, the math kernel library manual tells you not to use matrix sizes below 32 in each dimension. So this is one real problem. And there you can get to some theoretical limits. I will skip this part. It's obvious that you cannot split the training data into pieces less than one. So that's a natural limit. But we see that their limitations are starting much earlier. In a nutshell, basically, is that if the amount of compute you have to solve in one iteration is getting too small, it's not efficient anymore. So the outer parallelization is going to hurt the inner parallelization, and you're losing your speed up. Most people would suggest that just increase the size of the batches. Now, if small batches are bad, just increase them. There are two problems. The first thing is that the memory size of the GPUs is actually limiting the batch size. And the other one is that actually if you could do so, it also will hurt your accuracy. There's some particular details of the optimization algorithm that if you use larger batches, you will reduce the noise in your optimization problem, and this actually will cause it to converge to worse solutions. I will skip that part. Now, we don't know how to solve this yet. Many people are working on this, but let's assume we would have solved this problem. What would we see then? And this is the third part, which is very hard. And you will also know that from HPC, which is the data I/O problem. In the plots before, I didn't show you how long it takes to actually load the training data. We simulated that. We just took a machine with a very large main memory and put all the data and chunks in the main memory. But if you're trying to get the data from a distributed file system, you end up with something like this, spending like 80% of the time waiting for the data. And this is a huge problem. And if you hold the data locally in a single node on an SSD, data I/O is no problem. But even if you have the data on an SSD, if you use multiple GPUs, you will run in the problem that the SSD is not fast enough. So if you buy your 8 GPU box, you better start thinking about where to put the data. Because if you only have one SSD in there, or only you have 2 SSDs in there, that might not be enough to have a rate 0 to get the data up to speed. So there are several problems here. Okay. The other problem is with deep learning and file systems, and I'm wrapping up in a minute, is that the access pattern of a deep learning algorithm has to be randomized by design. You have to choose your samples by random, otherwise the algorithm won't work. You cannot have a stochastic algorithm which is not pulling its samples at random. Then you end up with huge access of many, many small files at random, and this is really killing your parallel file system. Just looking up the data will take up most of the time. And in this field, we're working on a solution based on our BGFS file system, where we're trying to have a temporary file system just for this training job, which will be spanned over the SSDs of the nodes. And you can actually have the file access patterns optimized just for this training run. And after the training run, we will throw this file system away. And in this way, we get a lot better performance. Again, details tomorrow on the poster. So let me conclude. The main problem with deep neural networks in a distributed environment, or even if you have just multiple GPUs in one box, is that due to the nature of the optimization algorithm, you end up with doing an iterative algorithm where the compute amount per iteration is so small that it's very hard to do this efficient anymore. And this problem is even getting harder and harder the faster the GPUs are getting. So now if we're looking for the next generation of GPUs, and maybe we expect another factor of 4, you might be happy if you're a single GPU user, but if you're a multiple GPU user, it's not exactly clear if you can benefit from this. And possible solutions are actually, and this is the main thing, the entire community is really working hard on new optimization algorithms. And I think the breakthrough here will not be in hardware, the breakthrough here will be in new optimization algorithms. So there are many, many solutions out there. I read about 5 papers per week with new suggestions. So far, there has not been a breakthrough, but I expect it soon, within the next year or so, because the pressure is so hard. And if you want to start now, what can you do? The best tip actually is start when you're designing your networks. Go deep. Avoid fat layers with many, many fully connected neurons. Maybe you can actually get rid of the fully connected layer at all. So that's actually possible. Google has shown that with their Inception module. So it's kind of insane. Now you have a deep neural network without neurons, but it works better. Also using networks with different branches, which can be parallelized in an easier way. And also try to optimize, and you always have to do a lot of parameter optimization. Try to start off with larger batch sizes and optimize the meta parameters to larger batch sizes, and not do that because you just have one GPU for design, and this one GPU only has 16 gigabytes of memory. You have to use a small batch size, and then you have an optimized model for a batch size of 32, and you're limited from the start. 2 more slides. I already mentioned that. We have a poster tomorrow. If you're interested in the technical details, you're very welcome to show you all these things. And the last point is deep learning and HPC communities are actually merging. And where's the community meeting? Maybe here next year again with many, many deep learning applications. Maybe someone's actually showing what they're doing. Would be very interesting. And just two more things. On the ISC, we have an entire day deep learning track with very good speakers, invited talks. And at the Supercomputing this year in Denver, there will be, for the third time, the machine learning and HPC workshop, which is up to 80% deep learning by now.
Okay, with that, let's thank our speaker.